probably go ahead and get started. We'll keep letting people pop in.
Yeah, numbers, we are at 42. People still keep coming in.
Well, thanks everyone for staying on. This is a pretty long workshop, and so yeah, that's great. A lot of you have stayed on, and we really appreciate that. And I'm sure Shuang does too, because what he's going to share with us is going to be really interesting and exciting. So Shuang Zhang is a postdoc at the Carnegie Earth and Planets Laboratory in Washington, D.C. And he's going to talk to us today about his really exciting work in cluster analysis and its applications in geochemistry. So he's going to go through a talk and he's going to do a tutorial portion, and then we'll have a Q&A. But if you have questions along the way, feel free to ask, and I'll interject them. You just ask them in the chat and I'll interject them as needed, or we'll get to them at the end. So again, thank you all for coming, and Shuang, you can take it away.
Sure. Thank you, Shauna. So Shauna, can you hear me loud enough?
I can hear you perfectly.
So Shauna, it's good to hear, right?
It's great.
Okay, cool. So hello, everybody. I'm really glad to have this opportunity to share with you some practices of using R and RStudio to do the cluster analysis. So I put my email here, shuanggang111@gmail.com. So if you have any questions afterwards, you can just shoot me an email. So my topic is cluster analysis and its application in geochemistry. So first, we want to know, what is cluster analysis? So by a very simple definition, to me, it's an unsupervised machine learning method to find groups in data. So cluster analysis try to group your data in different clusters in which the samples within the same cluster, they are similar to each other, but they are different to the sample or to the samples from the other clusters. So talking about the finding groups in data, I think most of you or many of you know there's another machine learning technique called classification. So the difference between clustering and classification is easy to understand. So the main difference is classification is a supervised machine learning technique, while clustering is unsupervised machine learning technique. So here I give you a brief example. So suppose we have like 6 samples, and 3 of them are cute cats, and 3 of them are cute dogs. And so for classification, we do know that they are cats and dogs. And based on the features of our input data, such as the body size of the sample, the ear length, the number of teeth, or the sharpness of the claws, or various different features, we can use classification to try to separate these 6 samples into 2 groups. So if after our classification analysis, we have now 2 groups. One group has like 3 dogs on the top, and the second group has 3 cats in the bottom. So we can compare the outcome, like 3 dogs in one group, 3 cats in one group, with the real sample labels, like 3 dogs in one group and 3 cats in the second group. So we see that classification has done a really great job here. So you can see it achieves 100% accuracy here. And then if we move on to cluster analysis, in fact, then we don't know whether these samples are cats or dogs during the cluster analysis, although in reality, 3 of them are dogs and 3 of them are cats. That's why during the cluster analysis, I turned the color into black and white, meaning we don't know which sample belongs to which. But fortunately, due to the really big differences between the features of cats and dogs, a good clustering algorithm should be able to separate these 6 samples into 2 clusters or like 2 groups. So if after clustering analysis, we have some results like this, like 3 dogs in one group and 3 cats in another group, we can see that, okay, our cluster analysis has done a good job here. But we cannot see that our cluster analysis is 100% accurate because we don't have any label to compare which category our modeling results belong to. But due to the big differences in the features of these 2 groups, we can say, okay, our cluster analysis has done a good job in like putting the samples in the same group that are very similar to each other, but the samples are very different across these 2 groups. Okay, so as you may already found out, due to the lack of data labels, evaluation of identified clusters actually requires domain knowledge, and sometimes it tends to be subjective instead of objective. Although I will show you later in the talk, there are several metrics or statistical methods to help you to choose the best clustering methods and choose the best number of clusters K. But the final decision really depends on the domain knowledge to see if the cluster algorithm is the optimal one or not. Okay, now we try to do the cluster analysis, and then we need to first pick up a coding language. So there are actually like many languages or like softwares can do a cluster analysis, but in the open source world, there are 2 most popular ones. One is Python and one is R. And we know like Julia, as Brian has mentioned, is also a good language and it's moving very fast. But for now, for the cluster analysis and many other machine learning techniques, and there are Python and R have a lot more like mature packages already. So I think that if you move into the field of data science and machine learning, you can pick either R or Python now. And frankly speaking, it's kind of hard to pick which one to use in the long run because they have their own advantages and disadvantages. But for me, I would suggest that if you have time, you should learn both. And I use both Python and R for different purposes. But in this practice and workshop, I picked R here, mainly because like 2 reasons. The first one is that ggplot2 is R, and the extensions related to ggplot2 are very powerful in visualization. And I know that the CBOY in Python is also great, but personally speaking, I think it's not as flexible as the ggplot2. And I know that there's a matplotlib in Python, and with it you can almost achieve anything you like. But to quick like visualize your data, I think ggplot2 is really great. And the second reason is that the data manipulation in R is more streamlined with 2 packages, dplyr and data table compared to Python. So we will use R here. And another reason I want to show you R here is that Chao give you an example using Python, and I think that different people have different preferences. So I pick R here to show you another opportunity if you want to stick to R in the future. And I hope I can show you many tips in data exploration and data visualization that can be useful in your future work. Okay, so I first pick R, then you need to pick an editor to write R code, and I pick RStudio. RStudio is an integrated development environment for R. And this is a panel for the RStudio. You can see it's divided into 4 panels. The top left one is the code editor. You can write your script in this section. And the bottom left is called the R console or like RStudio console. So you can see the output from your code in the code editor. And then on the right, on the bottom right, you can see this the plot panel. You can see that the visualization results or your plots can be displayed in this panel. I will also show you another way to see the figure using the zoom function in this panel. And on the top right, you can see this is a panel for where you can see all your variables in the current environment. Okay, let's move on to cluster analysis. And before you do cluster analysis, I would suggest that you can do a statistic called the Hopkins statistic. This can help you to determine whether you have any clusters in your data or not. So this statistic is very easy to understand. So basically, it will kind of randomly sample some data from your original data sets and compare the distance of the randomly sampled data to your original data set. And then you manually like create another subset of uniformly randomly distributed data called Y that has the same variation as the original data set, and you compare then you compare the distance between the data points in Y to the original points in X, and then you compare the two distances subset from the original data and manually created subset based on the original data. And you can see that each value that is higher than 0.5 tends to indicate that the data is clustered to some degree here. And I know that there are a lot of words here, and if you miss something, you can just return back to the video to see the detail of this Hopkins statistic. Okay, to give you a visual example here, I like created two data sets. The first data set, as you can see on the left, it has two clusters. It's very easy to see here. And if you use Hopkins statistic, you can see the H value is 0.89. And on the right, you can see there's a data set that is kind of looking like randomly distributed. You can see the H value is close to 0.5. Okay, so then you can see that by using the Hopkins statistic, you can see the clustering tendency in your data set. Okay, well, then if you want to continue to do the cluster analysis, there are many different types of algorithms in cluster analysis. And in this slide, I listed 4 of them. So you can see first one is centroid-based clustering, and a typical or a classical example is K-means. The second is connectivity-based clustering, and an example is hierarchical clustering. The third one is the distribution-based clustering, and very typical algorithm is called Gaussian mixture model. And the fourth one is density-based clustering, called DB-scan. It's density-based spatial clustering of applications with noise. It's a long name. So, and due to the limit of time, in this workshop, I will be focused on 2 algorithms. The first is K-means, and the second is hierarchical clustering. But one thing I should tell you is that the other 2 algorithms are also well implemented in R and also in Python. So if you like finish running these 2 algorithms, you're welcome to run the other 2 or the other many algorithms there. Okay. So let's move on first to K-means clustering. And if you look at the name called like K-means, it kind of looks like you kind of need to find like a K clustering based on some like a mean value or something like that. And specifically, the basic idea behind K-means clustering is as follows. So first, we need to specify the number of clusters. Here I use K here. and then you assign your samples to each of these K clusters so that the total within cluster variation is minimized. By seeing like a cluster within cluster variation, I mean that we can use the equation on the top to calculate the within cluster variation. So basically, for a specific cluster K, the within cluster variation is the sum of the squared distance of each data point in the specific cluster to the centroid of that specific cluster. You sum them up, you get the within cluster variation. There are different definitions for these within cluster variations. Also, some people also call it like within cluster variance, and this is one of them. And then obviously, total within cluster variation then means that you just sum up all the within cluster variation for each cluster from cluster 1 to cluster K. So in this equation, you can see the red is the within cluster variation, and the green is the total within cluster variation to sum up from K equals to 1 to K equals to K here. Okay, and then specifically speaking, I will show you briefly the algorithm of K-means. I think most of you are already familiar with this algorithm, but due to the wide range of audience, I think some people may not know. So this is just to refresh your memory. So the zero step, we need to specify the number of clusters here. Okay, and this is on the left. You can see our data. This is our data here. Okay, let's first like assign the 3 clusters. We assume there are 3 clusters in this data set. So we put K3. And then the first step is that we randomly assign a number or a cluster from 1 to 3 to each of these of the regions. So you can see there are 3 colors here, and each color represents 1 cluster. Okay, and after the assignment, you calculate the centroid for each color here. So there are like three points here. And then you begin to do the iteration until the cluster assignment stop changing. By doing iteration, that means that for each of the K clusters, you compute the cluster centroid like here, and then you assign like from here to here. You can see you assign each sample to the cluster whose centroid is closest to that sample. So you can see that in this step, you can see you have this like randomly distributed like green color, the more concentrated here, and the orange color here, and the pink color here. And then you recalculate the centroid, then you assign again to each cluster of the different samples. And this is the final result. You can see that these samples are already relatively good separated from each other. And then the algorithm will stop here. By saying stop, it means that the centroid will not change. It will stay in the same location here. Okay, so this is the basics of the K-means algorithm. But as we just said, we first need to specify a K value, meaning the number of clusters. But the question is how to choose the value of K. Okay, there are also a lot of methods to pick up the K value. And here I will show you 3 methods that I think that are very straightforward to implement and is easy to calculate. So the first one is called elbow method, and the details are as follows. The first step is you can conduct K-means algorithm for different values of K. For example, you give K from like 2 clusters to like 5 clusters, or from like 2 clusters to 10 clusters. And then for each K value, you calculate the total within cluster variation. And then you plot the curve of the total within cluster variation versus the number of clusters K. And then in that plotting, the location of the band, or you can call it knee in the plot, is generally considered as an indicator for the appropriate number of clusters here. Okay, I think here the an example to show you this method here. So you can see here on the left, we still have the same data sets as you already see just several minutes ago. And then you can add the elbow method here. And on the y-axis is the total within sum of squares, total within cluster variance or variation. And on the x-axis is the number of clusters from like 1 to 10. Okay, then you plot, you see this curve here, and you can definitely clearly see the elbow is here. So the knee is in the location of 2. And you can see that, okay, the total within variation actually is always decreasing with the increase of number of clusters you see here. This is very normal because you can imagine that the upper limit or the extreme case is that you assign each sample is to be its own cluster, right? If we have 10 samples, you have like 10 clusters, then the within cluster variance will be 0. So this curve will always decrease like toward to 0. But the most important thing here is that we want to find the knee of this curve, because as you can see here, from cluster 1 to cluster 2, there's a huge drop of the total within variation, and from 2 to 3 or from 3 to 4, there's only like a minor drop of the total within cluster variation, meaning that increasing the cluster number from 2 to 3 will not help much in reducing your total within cluster variation. So we pick 2 here. Okay, this is one method called elbow method, and the second way is called the silhouette. The silhouette value is a matter of how similar a sample is to its own cluster compared to other clusters, and it's also a very easy and straightforward method. And I don't show you the details to calculate the silhouette value for each sample. And you can see the details following this link. And below, oh, I'm sorry, the mouse is a bit tricky here. And below you can see there are like 4 steps to calculate the average silhouette for our cluster analysis. You can see these steps are like similar to the elbow method. The first step is that you conduct K-means algorithm for different values of K. The second is that for each K, you calculate the average silhouette width of the samples. And third, you plot the curve average silhouette width versus the number of clusters K. And then this time, the location of the maximum is considered as the appropriate number of clusters here, meaning that with this maximum silhouette width, you can see that the samples in the same cluster are close to each other compared with their distance to other samples in the other clusters. So this is the meaning of the location of the maximum. Okay, so now you can see this is the plot for the average silhouette, and on the left is still our data set, and on the right is average silhouette width here. And you can see from here, the maximum location is number 2, means that the number we have the 2 is the best value to be picked as our best number of clusters here. Okay, and then I also want to show you a third method. I recently see that it's kind of good to assess the stability of your cluster analysis. So we can finish this by resampling our data set and compute an index called like G-card index, and the higher the better. A higher G-card index means that the randomly resampled samples, when you conduct cluster analysis on them, they have similar clusters compared to your original clusters that you get by conducting cluster analysis on your original data set. So a higher value means our cluster analysis is relatively, and our samples themselves are relatively robust to this cluster analysis. So you can see the value, the highest value is 2 here, meaning that 2 is also picked based on this cluster stability assessment as the best number of clusters here. Okay, now we finish k-means, and we will move on to hierarchical clustering here. And I will use one type of hierarchical clustering. This is called agglomerative clustering. This is a bottom-up clustering, and you can see what I mean in the following. So the basic idea behind the agglomerative hierarchical clustering is also very straightforward. So in contrast to the k-means, which we need to first specify the number of clusters in the first hand, now we just treat each sample as their own cluster. So each sample is one cluster. And then moving forward from this step, in the next steps, we will like combine the two clusters that are most similar to each other into a newer, bigger cluster. And with the time going, with the steps, step by step, you will like gradually building like a tree-like structure for your whole data. So two samples cluster to each other. If these two clusters may combine with another cluster to form a big one, then you like move forward. You will first achieve a single big cluster after the iteration here. And then you will find that in the second step here, you can see that we need to find the most similar clusters. Then you may ask, how do we define which two clusters are most similar to each other? And the method here is relatively kind of messy, but actually it's also very straightforward to understand. By saying messy, I mean there are different types of measurements of the similarity here. And here we call a thing called like linkage to measure the similarity between two clusters. Okay, so here I listed like 4 types here: minimal linkage, also called like single linkage; the maximum linkage, also called complete linkage; and the third one is average linkage; and the fourth one is Wald's criterion for calculating the linkage. So there are also other types, and I just show you these 4 popular ones here. And by like seeing like a minimal linkage, as we check these 2 clusters, cluster A and cluster B, the minimal linkage means that we choose the minimal distance between these 2 clusters. You see here, this point is close, very close to this point, and this distance here is closest the distance between each pair of the points. Okay, so this is a minimal linkage. And then this is a maximum linkage, means that this is a maximum distance between these pairwise points between A and B. You can see this point and this point is the maximum distance. And the average linkage, you calculate the pairwise distance and you do the average here. You can see here, there are many lines here. And the Wald's criterion is that, okay, if you already have cluster A and a cluster B, then if you combine them together, then you need to first calculate the within cluster variation in cluster A. You calculate the within cluster variation for cluster B, and then you calculate the within cluster variation for the combined clusters A and B, and then you calculate the difference of the sum of the cluster within cluster variations in A and B, and the total within cluster variation when you join them together. So these are kind of like 4 types of linkages that can help you to determine the similarity here. Okay, now I think an example is more helpful than words here. So I will show you an example of using the minimal linkage here. Okay, assume you have 5 points here, 1, 2, 3, 1, 2, 3, 4, 5. And when you use minimal linkage, the first step is that, okay, you calculated the pairwise distance for each of them. And then you see this distance is the is the smallest. Then you group 1 and 2 into a cluster. You can see here, you group 1 and 2 here. And this line, the height of this line is the distance between 1 and 2. Okay, now we have 1 and 2 in the same group. We call it one cluster. And this is another cluster, and another cluster, okay? Then you calculate the single linkage between each of these clusters. You can see this is the minimal distance using the minimal linkage here, okay? Then you group these two together, you put it here. So 3 and 4, you form a cluster here. And the iteration 3 is that you calculate the minimal linkage again. You can see these two clusters are closer to each other compared to this cluster, and this cluster to this cluster, okay? Then this is a minimal distance between this cluster and this cluster. You put the height here, and then you combine these 3 samples together. Now you have a bigger cluster here. And then the next step is that, okay, now we have like one cluster. You calculate the minimal distance of the between the pairwise samples, which is the meaning of the minimal linkage. You find the minimal distance here. You put the height here. This is the height of this distance. Then you group these samples together. Now you have one big cluster here, and we call this tree-like feature as to be a dendrogram here. Okay, this is the full process of doing the hierarchical clustering here. And then you can pick which linkage criterion you want to use, right? There are single or like minimal linkage. There are like maximum linkage, or like you can call it like complete linkage. There are average linkage. There are walls criterion. So the problem is that which one you want to pick. Okay, there are also several methods, but 2 methods I think that are useful are like this. Method 1 is you can use a statistic or called like a coefficient correlation to determine which linkage you want to use. So this coefficient correlation is the measurement of how physically a dendrogram preserves the pairwise distances between the original unmodeled data points. And the higher the coefficient correlation, the better, meaning that it represents better of the original structure in your data. And the method 2 is that you observe the dendrogram to see if the tree is in a relatively balanced shape. Okay, and in the hands-on practice, I can show you how to calculate the coefficient correlation here. Okay, and then after you get in the dendrogram, the question here is how to get the clusters, right? So this is actually very simple. You can just put a horizontal line, means you cut the dendrogram in different groups. For example, if you put a line here, then you will have one cluster here, and the second cluster here. You will have like 2 clusters here, right? One has 2 samples, another one has 3 samples. You can also put a line here. If you put the cut here, there will be 1, 2, 3, 4, 5. And then you can see that each sample forms its own cluster here. Then the same question occurs, which is how do you pick the K? Although, as we already said, the hierarchical algorithm doesn't need the specific find K in the first hand, but to get the specific number of clusters, you still need to pick the best K after you finish constructing the dendrogram of using hierarchical analysis. So there are also several methods, and I will show you the same methods when we compare with K-means. The first one is elbow method here, and you can see for the hierarchical cluster analysis, you can also calculate the elbow here. This is also 2 here. And then there's another method. It's also the zero A method here. You can set the cluster 2 gives you the highest value here. So cluster 2 is the best. But you can also use the G-color index to indicate what is the best cluster, number of clusters. And you can see here 2 is still the best. Okay. Okay, so then we finished the discussion into k-means and hierarchical clustering. And now I will show you an example in geochemistry here. And now I will pick the paper by Daniel Gregory from the University of Toronto. And he compiled different types of pyrites. So a lot of pyrite types belong to the all deposit type. And the other type of pyrite belong to the bearing sedimentary pyrite type. And in this paper, Dan used a random forest, which is supervised machine learning technique to separate these types of pyrite into different groups, and it's a classification problem, supervised machine learning, and specifically the algorithm is random forest. And now, for comparison and to do our cluster analysis, I picked two types of all deposit related pyrite, and one bearing sedimentary one type that is a bearing sedimentary pyrite from the original data set of Dan, to show you the example of using cluster analysis in the geochemistry here. And for the all deposit related pyrites, there are two types. The first is VHMS, called volcanic hosted massive sulfide, and the porphyry copper type. And for bearing sedimentary pyrite, it is bearing sedimentary pyrite. And each of them, I picked like 30 samples. So in total, there are 90 samples. But to do the hands-on practice, I deliberately added like two random samples with missing value to show you how to get rid of these missing values. Anyway, this is a brief introduction to these three types of pyrite and the bearing. They form in different environments, and for the bearing sedimentary type, is formed in the shallow marine sediments with a relatively low temperature. And for this VHMS, which is volcanic hosted massive sulfide, it is created by volcanic associated hydrothermal emits in the submarine environment. So it's linked to a medium temperature here. And the final type is porphyry copper. It's associated with igneous intrusions, and so it's related to the high temperature here. Okay, now we have three types here, but keep in mind that in a real clustering analysis, you might not have any label at all. I picked three samples here to try to see if cluster analysis has the ability to separate our samples into these three clusters, or to some like interesting types of clusters, just to make a comparison. So we can call these types as external labels for our data set. Okay, in this workshop, you will run RStudio, and you will see a lot of data exploration techniques, especially the data visualization. I will show you a lot of tips to produce elegant figures that are ready for publication, or you can modify yourself. And then most importantly, the hands-on cluster analysis with pyrite samples. So now we'll move on to our data analysis, and I will continue, and maybe I will answer some questions in the end. So I guess most of you, or all of you, have already have these files. I put some extra files here, but like the test here, you can ignore this. So mainly there are like 4 files here. First one is called cluster.html. Second one is called cluster.r. Third one is called cluster.rmd. And the fourth one is our samples. I just put them all together in the one folder, but in practice, it's better to separate your files into different folders. For example, you can create a data folder, and then you put your pyrite samples into that folder. And then you can create a code like R. You can put all these R file into that folder, and you can also create an output file, and you can put this cluster.html into that output folder. Okay. So Shauna, is everything all okay now?
Yep, everything's great. We did have one question if we wanted to address it now, or we could do it after the
Sure.
tutorial. That's
Is it related to the cultural analysis or related to the installation of the
it's
software?
related to the cluster analysis. So I'll ask you the question and you can decide if you want to address it now. So the question is, what about fuzzy versus hard methods, as both hierarchical and clay means clustering are by default considered hard?
I think that's a good question. And we all know that like k-means, there are like fuzzy k-means. And also in this talk, I listed like several techniques, additional techniques like Gaussian mixture model and DB scan or HDB scan. Although like DB scan or HDB scan, they are not, to my knowledge, they are not like soft clustering. But Gaussian mixture model is also another method to perform the soft clustering. I think whether you pick hard clustering or like soft or like a soft clustering really depends on what you try to do. And also I didn't talk much about the k-means and the difference between k-means and hierarchical. And in addition to the soft and hard clustering, although like the normal k-means and hierarchical clustering are not like they all belong to the hard clustering. But even for these two, there are a lot of difference between the two. The big difference between k-means and hierarchical is that k-means is kind of a flat clustering. You specify like 3 clusters, you have 3 clusters. But hierarchical is built from a single cluster for each sample to one big single cluster. So you can choose where you cut your trees. So you can see, you can have like clusters within clusters if you want to understand the structural or hierarchical structure of your data points. So this all comes to what you want to achieve. If you really want to see, okay, I want to determine the probability of each point that belongs to which cluster, you can definitely use soft clustering, like the fuzzy k-means or like Gaussian mixture model. If you really want to have a hard clustering, you just use like hard clustering. And also in the same process, I think the data visualization is really important in the clustering analysis. That's why I put a lot of efforts in this R file to help you visualize your data either in a lower dimension or a higher dimension. So all these come to a kind of combination of like a trial and error and your own desire and your domain knowledge to pick which one you want to use. I think I should stop here. Yeah.
Great. Thank you, Shuang. And so I think we can move into the tutorial stage of the presentation. If anyone has questions, feel free to type it into the chat and we can interject. So I think this part will be a little more.
Sure. Okay. Thanks, Jonah. So I think we don't have much time left to do the practice. But anyway, I already produced the HTML file. This is the output from this file, from the RMD file. So as Shona and Charles, they both mentioned that the Jupyter notebook is a good way to share your code. But for R, I think R Markdown file, which is called the .rmd file, is also a good way to share your code. And to share your output, we also have good method in R is that you can, you can use this like R Markdown file here, as you can see here, .rmd. You can see this file is a bit different from your normal R file here. This is .r, this is your normal file, and this is your R Markdown file. You can see in R Markdown you have different lines of words to tell you the name, the output, the version of the output, and these different styles. And then if you use like neat here, I can show you here. This will, in my computer, it take like within 2 minutes. So you can see the output in the R Markdown console here. I hope it will finish soon. It's only like 2 minutes. And in the meantime, I will show you this like R file. This file is generally what you will work with in your own project. I mean that if you don't want to share with people your R file, or you are only in the development process, you can totally use the pure R file here. And this is a full code. And to generate, let me see, the output of all these analyses. It has like just to show you, it has like a little more than 1,000 lines of code, and you can try to put some like code into one function to reduce some of your code. But anyway, for simplicity, I just write all the code here. Okay, here within like 2 minutes, you can see we already have the file output here. And you can see this is a .html file here. And you can see the R Markdown file, the file generated from R Markdown. You can also generate index here. If you click any one of them, it will jump to the part of that code that you are interested in. So that means that this output is really a good way to separate, to share with your co-authors, or share with your students, or your colleagues what you get from your analysis. And this HTML file is a static file, meaning that you cannot run code in this file compared with the Jupyter notebook here. Although you do see some like for example, to visualize the 3D format, you can see you can zoom in and out here. See, using the package plotly to see your output here. But for the other code, you cannot run here. To run the code, you can either run in the R Markdown file, RMD here, and then you can generate the HTML file again. Or if you want your colleagues to run the code, you can just send them this R Markdown file, so they can run the code themselves, or generate the HTML file themselves. Or you can share with them the pure R code here. So I don't think we have much time left, although I'm the last one to give the talk. So basically, I can show you briefly what I'm doing here. So first one, you load the package here. This is check if there's no package, you install your package. And then you set up your working directory, and then you read in your data. Then you check the dimension of your data, which is 92 rows, 11 columns. You can check the structure of your data using the str function. And this is all the columns. And then you can check the names of your data frame. Okay, as you know, we use trace elements as the cluster analysis of Pyrite. You can plot the missing of data, because I deliberately added 2 missing values. You can see for antimony and copper, there are 1% missing value. For simplicity, you just use any.omit to delete all the any values. You plot again, there will be no missing value here. But in practice, you need to consider whether you want to fill these any values with some values with a reason to keep as rows as possible, or you just want to delete them. So you can check the types of Pyrite here. Okay, there are like 3 types here, and why not give them some color? Because we know like a sedimentary type, Pyrite type is in a low temperature environment, VHMS in a medium temperature, and porphyry in a high temperature. Then you can give them some color. You can have these 3 colors here, and also we can also rank our types from low temperature to high temperature here. Okay. Then to plot the distribution of your trace elements in these pyrite types, which we use these trace elements as features, you can transform your data frame from the wide format to a long format. Then you can calculate the histogram for each element here, and then you can also separate these types in their own panel here. So okay, so I run this code here just to give you a feeling of how you run the code in this R Studio here. And there are some like shortcuts to run the code, or you can just click code here, and then you can like run select lines to run. And in my case, in my Mac, I use command and return. I can run the code. Okay, then you can you can continue to run the code. And if you already see the HTML file, you already see all of them here. I just want to go through some of them so that you have a feeling to work in the R Studio. Then you can also do the log transformation to this data. And you plot these histograms again here. And you can also see the figures here are not ideal here, kind of like a compact. You can just use zoom. Just use get the data out. You can make it bigger. And my code here is optimized to give you a good look when I transport when I like export the figure or the output to the HTML file. So, but you can always change, as you can see, the text size, the label size to make it good looking in your own laptop. Now you can save the figure. I don't show you the command of how to save the figure in your own computer. For the ggplot, here the ggplot, you can use ggc. Okay, then this is the pair plot, and this is a trick to make them feel all the color that you want, because the default GG pair plot, the pairwise plot doesn't have that functionality as far as I know. And now you feel the okay, here it's finished. You can also zoom in to see these the three types here. And this is the scatter plot. This is their own distribution for each type of pyrite for each element, and this is a correlation between each other. And I think I need to go quickly. This is a basic statistical analysis. You can always add your own lines of code to make the figure as beautiful as you like. And I think what I want to show you is something I didn't talk about. It's the PCA analysis, the principal component analysis. So the reason why we do PCA is that there are several reasons. One reason that you want to visualize your data, that if your data is high dimension here. So if the logic is very simple here, okay? For example, if you look at this HTML file already generated for the single element, you can just do the histogram plot, right? This is like called 1D plot. Then for these two, if you want to compare these two elements, you can do the scatter plot here, okay? This is called a 2D plot. And then you can also, as you see later, if you have like, if your data set has like 3 dimensions, you can do the 3D plot. But as we all know, the 3D plot is already relatively complicated. But imagine if you have like more than 3 dimensions, like 4D, 5D, 6D, or like 10D, more dimensions than that, how do you plan to visualize your data? Then the method called like PCA is a linear dimension reduction method, and there were other good methods to reduce your dimension, like Kisney, which is also a very good method here. But here I use PCA here. You can reduce the dimension to like 1 or 2 or 3 or 2 like the original dimension. Here we have like 10 trace elements. We have 10 dimensions here, and then each dimension will explain some proportions of your variance in your original data here. You can see that the first principal component or the first dimension is displaying almost like 60%. Then you can make the cumulative proportion. I mean, if you add up the proportion of variance explained by the principal component 1, principal component 2, you can explain almost like 75%. And this is the contribution this is a different the contribution of different elements to this to your PC to the PCA result here. And this is contributing to the principal component 1 dimension here. And you can also check the contribution of each element to the dimension 2 here. And then you can do a lot of things like the biplot. This looks complicated, but actually it's not. This is principal component 1 dimension. This is the second dimension. You can see your data. You can know that's what I mean, that you can visualize your data by reducing your data point from 10 dimensions, like 10 trace elements, into like 2 dimensions, principal component 1, principal component 2 here. Okay, there are a lot of details you can find here. Means these elements tend to form the Owen group in this PCA analysis, and these 2 elements, Cobell and Nickel, form the Owen group. I write in the HTML file some notes of why these 2 groups are different. That's because their concentration are different among these 3 types. And the behaviors of these different element concentration are different among these 3 types, and these groups tend to go together, while these 2 kind of different from these concentrations. That's why this is in one group, this is in another group. Okay, then you can go along. I hope to finish quickly. This is without these arrows. Now we reduce our dimension to 2 here. And you can also see, okay, if we want to see the third dimension, like one dimension, 2 dimension, 3 dimension, you can using these, using Plotly to see this result here. Okay, and PCADF, yeah, you can see here, this is the first dimension, second dimension, third dimension. We use Plotly package to get the 3D plot. Okay, then as I see, you can use Hopkins statistic to check if your data has any clustering in it. And here our value is 0.7, means, okay, they are kind of relatively clustered. And also you can see, which is a good way to show you here, that you can see maybe there are some clusters here, but they are not as good clusters as the samples I show you in the talk just like 10 minutes ago. You can see they are kind of loosely clustered here for our sample. So that's why this value is not that high. But anyway, we can still do the cluster analysis, and this is the F with NG class function to draw the within to draw the elbow cloud here. And you can see this is to draw the silhouette width of our samples. And then this is the G-cut matrix to calculate the stability of our clusters. You can see it run pretty quickly because we only have 90 samples. in our cluster analysis. You can see the second is also the best. So okay, you assign 2 as the best here. Then you can, okay, you create some colors to your cluster. Okay, this is the cluster generated. So I think almost finishing for k-means, and we'll stop at k-means because hierarchical the procedure is kind of similar to k-means. But you can see here, you can see we have 2 clusters here. And the first cluster, most of the samples are porphyry copper, and the second cluster has the mixture of sedimentary and VHMS. This is not too bad because we successfully grouped the porphyry, the high temperature, into almost its own cluster, and this low to medium temperature part into their own cluster. So you can plot. This is another way to visualize your cluster analysis. So you can see these 2 clusters, they are good separate weighted for these 8 elements, but for the cobalt and nickel, you can see there are mixtures between these 2 clusters. Okay, then you can do like GG pairs again, and this time we don't use the original types because in reality we don't know the groups at all, whether they belong to VHMS or sedimentary or like porphyry copper. So now we just do the GG pairs for let me see. Okay, here we have it. You can see these 2 clusters similar to the line plot just before. You can see for these like 10 elements, they are kind of relatively good separated from each other. But for these 2 elements, these 2 clusters have a lot of mixture here. Okay, and then this is a way to show how our cluster results compare to the original types. This is called external variation, meaning that in your cluster analysis, if you know what types of your samples belong to in advance, you can use the cluster results to compare these results to the original types. And in our case, the original types is our parent types, and then we compare how similar the original groups are to the cluster results. So you can do this, and this is adjusted rank in index, and you can see if we pick 3 clusters, then the one index is high, meaning this is a very good reproduction of our original types. By saying reproduction, I mean the groups generated by cluster analysis is similar to the groups in the original types, and the 3 is higher than 2, 4, 5. If we use a 3 here, I can show you quickly. Okay, this is our using k-means, we generated the 3 clusters. And then we can do all the plots again. And as I just mentioned, if you want to reduce the lines of code, you can generate some functions to reduce the lines of code to use the same function again. And you can see, okay, this cluster now have most of them are sedimentary type, but some of them have VHMS. I'm thinking of a pure VHMS, which is good, separate VH and part of the VHMS from this cluster. And the final 3rd type is almost all the porphyry types. So the 3rd, so it means that if you use 3, it is also good. And although the metrics told us that 2 is the best. So this is the GG product again, and this is the HTML here. Here, this is okay, and then we will move to hierarchical clustering, but there's a theme. They are very similar to the k-means. So I think I should stop here. and you can practice on your own. And I think I stop here. And if you have any questions, just let me know. Thank you.
Great.
Yep.
Thank you so much, Shuang. That was so informative and really clear. I appreciate that. So we do have a couple, or we do have one question, and that was basically, should we use PCA, or you could also think about using random forest, or just looking at, you know, which variables in your data don't exhibit a lot of variance, to reduce the dimensionality before clustering. So data, you know, should we use PCA or before? Or should we also, I mean, I guess you could do this kind of iteratively, right? You could kind of look at the cluster analysis and then go back. What do you think about that?
Yeah, I think that's good point. That's good point, because it's always tricky in dealing with cluster analysis. I would see that if you have a huge number of features, for example, if you have like 100 features, especially in your gene and like a gene expression analysis, I will highly recommend you use the PCA or some other dimensionality reduction method to reduce your feature space from like 100 or more than 100 to like a smaller number of feature space. They have like two advantages, I think. The first advantage is that it can greatly save your time of computation. If you have like more than 100 features, if you have many rows, if you run on your own laptop, it will take a lot of time to finish almost any clustering analysis. But if you reduce to like 10 or like 10 or like 8 or like fewer than 20 feature space or like dimension space, your algorithm will run much faster. And the second advantage is that it can reduce the problem of the curse of dimensionality, meaning that if you have a really huge feature space, as you already know from this talk and this hands-on practice, the measurement of the similarity between points are largely dependent on their criteria called distance. If due to the curse of dimensionality, you have huge feature space, the distance among each data points will become very similar to each other. So it's kind of hard to distinguish these points into different clusters based on the distance matrix. So if you reduce it into like 10, for example, 10 dimensions, I think it might behave better compared to the original data space, even if your time is not a problem. But if you have time, I do suggest you perform both to see if PCA can help improve your model accuracy. I think this is my suggestion. Yep.
Okay, great. Thank you. So we have a couple of other questions. I know we have the room until 3. I hope it's not going to cut off at 3. We can keep going for a little bit and hope it doesn't cut off on us. So the first question is, in this case, the multiple techniques the multiple techniques you use to choose the clusters, you know, elbow, silhouette width, and so on, seem to agree that 2 clusters were good. But what would you do in the case in which, you know, the elbow method suggests 2 clusters and the silhouette method suggests 3?
Yeah, this is a very tricky one to deal with. To me, personally speaking, I will prefer the silhouette method because I think I can share with, let me see, share with you this screen here. Okay, first I think to make things clear, I think I will start from here. So, okay, if you have a really good data set that is very easy to separate like this, right? Then if you use elbow, no matter whether you use elbow or like a silhouette, it will always give you 2 at the best because it's very obvious that 2 is the best, but this is the best scenario case. But in our own data set here, let me see here. Okay, I think this is a very good example here. Here, if you look at this figure, actually it's very hard to pick whether 2 or 3 is the best. Although from like 1 to 2, you can see there's a huge drop of the within cluster variance. But from 2 or 3, there's also not a small drop in the within cluster variance. Even from 3 to 4, there's also a drop. Although you can see from 4 to 5, they are kind of relatively flat. So it's kind of actually hard to pick whether 2 or 3 or even 4 as the best for the elbow method, because it looks to me it's not quite clear here. But the silhouette method here, you can definitely see the best cluster here. The number of clusters is 2 here. So that means that, okay, I'm not meaning that 2 must be the best, because as we know that cluster is not, it doesn't mean it's like 100% right. It just means this one might be the optimal structure of your clusters regarding to your own data set. And the silhouette method is definitely sees 2 is the best because 2 is the highest. So there's not many like subjective behaviors you can put in this silhouette method. So personally, I prefer silhouette, but keep in mind there are also many different techniques to use to tell you which one is the best. And in R, if you use R, there's a package called MB class. It has like 30 metrics to tell you which one is the best, and different metrics might give you different best number of clusters. But using majority voting, you can pick the number of clusters that is determined most times by these like 30 metrics to use it as the best number of clusters. So, and also you can see here there's another one. This is a stability analysis. If you really care about the stability, you will also consider this index, and it is also possible that this index can give you a different value of the best number of K. And also, if you have the external labels, for example, in our sample, we have three types of pyrite, and if we really want to force our clusters into 3 types, because we know there are 3 types, you can use the external validation to see if you force them into three clusters, whether they are good or not. So I can't guarantee that you will have the best number of clusters, but my suggestion that you try them yourself and combine with the domain knowledge and to combine with what you want to get the best one, or to get the optimal one. Yeah.
Thank you, Shuang. And you bring up a good point there, that having some domain knowledge is really important in interpreting these data, especially, I mean, if it's unsupervised, you really need to have some knowledge of what's actually happening here and what you expect to see. So that's where it's really nice to be someone who, like Shuang, has expertise in both earth science and data science, or having an earth scientist working alongside a data scientist is really important. So a couple of questions, and one thing, if everyone could just go to the chat, you'll see that Lucy has put a link in there to give some feedback for what you thought about the session and the virtual workshop and how it worked. Your feedback would be really helpful. So if you wouldn't mind clicking on that and filling that out, that'd be very helpful for us. And so I have 2 more questions for you, Shuang. I'm actually going to ask the second one first because I think it's a pretty quick one, and the second one will have, or the first one will have a little more discussion. So the second question is, Once the clusters are identified, how can we interpret which data points are members of the cluster? For example, how do we know that data point number 1 is a member of cluster X and not cluster Y?
Oh, this is a very easy question to answer, but I think maybe your question is not simply like this. Okay, so once the clusters are identified, it's they are identified, meaning that each label is already labeled. Each sample is already labeled as cluster 1 or cluster 2, and I can show you here. Maybe this is better using the HTML file. And so, for example, if we use K-means here, okay, here, I can put it here. Okay, so this is a K-means clustering algorithm. You give 2 at the best, right? Then you use it like E-class. There are many like packages in R that can do K-means clustering, and this is one of the package. Then you have K-means out best, and this K out means best will contain the labels, the cluster 1 or 2 or 3 for each sample. I think this is all. I think this is the answer to your question. But also, I think if you extend this question means if you have new data points, which cluster it belongs to, right? If you have some of the new data points, and if you already trained your cluster analysis in your older data points, in K-means there's also a method that can help you to assign the new data points into the old clusters you have. Or since you have like new data points, I would suggest you can just throw your new data points into your older data points, combine them together to redo the cluster analysis. Because it's unsupervised machine learning, and I think the more points you have, I think the better you will see the internal structure of your data. Yep. Is that helpful?
That's very helpful. Thank you.
Mm-hmm.
And okay, so the last question, and Ian says thanks. So the last question is basically about the number of rows versus the number of features. So I know this is a common question. And basically, you know, how many samples do you need by the number of features that you're trying to analyze? So, you know,
right.
do I need, I think you know what I'm asking.
Yeah, right. Yeah, this is a typical question in machine learning, and I don't think that it's easy to answer because it really depends on how many data you can get, right? I mean that you can always perform machine learning on the data you have, but there are some like rigid limitation for specific algorithm. For example, I mean this is a unsupervised machine learning, right? But talking about if we extend to supervised machine learning like linear regression, the number of samples must be greater than your like rows of than the columns of your feature, because if it's smaller than that, you will not have an answer for the coefficient of the linear regression. But generally speaking, except for this rigid algorithm, I would say for supervised, both supervised and unsupervised, if you can get like at least like 5 times or like even 10 times of your data points, I think that might be a good start. I don't think there's a hard rule to how many, I mean the ratio of the rows to your columns that you can use machine learning, or whether it will perform much better. I mean, but the bottom line is that the more data you have, I mean, the more rows you have, the better. Yeah.
Great. And just to make sure I understand, you said probably you need 5 to 10 times more rows than you have features? Or did I misunderstand?
Yeah, this is my own like rough standards actually, because it totally depends on if you have only like, for example, you have like 4 times of the data points, 4 times data, your data points is 4 times than the column numbers. If you want to perform machine learning, I think you can try what it can give to you. Yeah.
Great. So that's a good point. So what I'm hearing from you is you can try it, and you just need to, be really rigorous and looking at the different statistical tests that you showed us today, just to make sure that it makes sense to use this method for your data. And if you have too many features, then you need to really think about some of these data dimensionality reduction techniques.
Right.
That's what I'm hearing. Okay, great. Perfect. All right. Well, thank you everyone for sticking around. We ran a little bit long, but I really appreciate everyone's interest, and a big thank you to all of our speakers who really made this a fantastic session. And of course to my co-organizers. I don't know if Kirsten wants to say anything or Lucy wants to say anything, but we're going to send out an email follow-up after this with just some information so that you guys can follow up on Discord if you have more questions and have a nice discussion there. So please, reach out if you have any questions, but you should be receiving an email from us. And Goldschmidt started 6 minutes ago, so everyone enjoy. Sorry we can't see you in Hawaii.
And thank you from me too. Absolutely, this was great. And I appreciate everybody's feedback that's already coming in. And we hope to stay in touch with you and set up that webinar series in the near future. But in the meantime, use the Discord channel as Shauna already said. So thank you. And some of you can finally go to sleep and others can start the working day. Take care, everybody.
Cool. Take care. Thank you.